Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Laden Yuracek.
Journal Club was intracortical microstimulation modulates cortical-induced responses. Thais Benjamin Voigt, Pasandhya Astaigo Sigiri Yusuf, and they Kai Krau.
All very difficult names to pronounce.
Very difficult names.
It's fine.
What was the paper about?
So, I guess let's start at the beginning. The authors were attempting to essentially look at the response on a micro-ECOG from induced, or should I say, the induced response on a micro-ECOG from microelectrode stimulation on a depth electrode. So that's pretty much the broad, sweeping view of what it is that they did. I don't want to really get into the specificity or specifics, better said, of the auditory stimulation because I'm not anywhere near an expert in auditory precepts or things like this. But yeah, I mean, this is a complicated experiment to say the least from the auditory end. I can say what they did was great. I mean, we've attempted to do similar things with different type of device, magnetoencephalogram. So a MEG device.
In this lab?
In this lab.
Oh.
That was one of the first projects that I worked on. And that's about as specific as I can get because it was a DARPA-related project. So,
if you tell me, you have to kill me.
Yes. No. But yeah, what these authors were trying to achieve is not anything particularly simple. We can actually see the paradigm in figure 1, where they have pretty much a strong summary of everything they did. We can see the micro-ECOG on the cortex, and we can see the depth electrodes penetrating through the center of the ECOG. Figure B shows how everything is set up from a recording and current source perspective. We can see the current sources there in the center between the electrodes. So it's set up for both recording and stimulating. And then in C, part of the figure, we can see the auditory and electrical precepts for stimulation. So, I mean, it seems fairly simple in concept, but extremely complicated as far as actual execution. I mean, being able to do this is definitely a very highly skilled endeavor. So there's that. They actually did a very good job of reporting to the best of their knowledge what layer, what electrodes were in. So that's great. I mean, you know, this is extremely important for understanding what type of the response they're getting from their stimuli and what they expect to record as far as neural activity, spiking activity, things like that on the depth electrode side. The ECOG side is a little simpler in that respect, considering you're looking at broad spectrum information. But nonetheless, I guess that's an overview of what their experimental setup is. Where would you like to go next?
I don't know. I mean, we did really like this paper because it was so involved and because that it was so like well done, like each step was well done, something like this, or because then I mean the thing that I remember too was sensing and then stimulating is something that's not usually done, or when you do, then you have big artifacts that happen from that, right?
Okay, so stimming and recording. When you stim and record simultaneously, you know, if you think about what you're doing, you're essentially dumping tons of electricity into the brain in a very short period of time. And, you know, you cannot care what you're doing and just take it all. There's a likelihood that you're going to rail your amplifier and you're just going to saturate it. And what that space will look like, unless you have it properly set up, is essentially just either the max or the min of what the amplifier can display, what its resolution is. So stimming and recording, not necessarily simultaneously, but I guess synchronously, is extremely difficult. So the fact that they had a setup where they could do it, I think one of their figures shows their stim and record. Well, I suppose not. But essentially, stimming and recording and getting that really fine resolution in time is very difficult. So I think their earliest response is within 10 milliseconds, which is wonderful. It's something that you would expect. And the fact that they don't have a huge amount of noise within that 10 millisecond window is great. The noise, at least from saturated amplifier or from ringing, things like that, are always very visible when you have a biphasic monopolar stimulus. Essentially, you rail the amp up, you rail the amp down, and then the oscillation as the amplifier dumps current, things like that. You'll always see it. So the fact that they have very low artifact signal is great. The figure I'm looking at now is only for the auditory evoked potentials, but it's still pretty nice to see. I would like to find a figure 3 of 7 we see that they don't really have a huge amount of artifact. At least it's manageable. So that's great. But yeah, the fact that they could do something like this was difficult, to say the least, and being able to do this within the confines of an auditory paradigm it's a challenge, to say the least. It's a very difficult thing to do. So the recordings look good. From what I could see, the recordings look good, and I just can't say that they did anything wrong. There were some things that were a bit of an anticipated result, but the fact that they got an anticipated result is not necessarily a bad thing. It just means that they did something right.
So what would it have looked like if they didn't do, if they didn't do things correctly, if they were, if they didn't get good recordings? What exactly would you expect in that case?
Oh, I guess if we looked at the electrical trace, things I've seen, and filters can do funny things. Filters can do funny things to your trace, but some things that you would see are like a lot of high frequency oscillations after the stimulus. Mm-hmm. So essentially the trace goes up, comes down, and then oscillates quickly afterwards as essentially that's hard to say. I know some companies, like I believe Ripple, they have a technique built into their device called fast settle, if I remember correctly, which settles out that ringing within, I think, like 2 milliseconds. So essentially, I don't know how their technology works, but in general, I think what it does is it levels out the amplifier much faster. So you essentially don't really rail your amplifier the same way. So I'm not sure how Ripple's technology works, but 1 to like 4, 5, maybe even 10 milliseconds. It all depends on your system. So you could, it could be drawn out or it can be very fast. There are a lot of people that would like to stim and record simultaneously. So there are techniques to, deal with that.
And so you're saying like, okay, well, Ripple has a good technology, which is within 2 milliseconds you can settle, but then 5 is still good? Or, because this sounds like it was 5, wasn't it? Isn't that what you said, or how much did you say?
Oh, no, less. It was much, it seems like it was less than that. I actually don't know the exact number. I didn't see it in the paper, but it was short enough that they could look within 10 milliseconds. And, as far as conduction and jumping synapses and things like that, 10 milliseconds is a fairly fast response. And the fact that they show the auditory stimulus, what the auditory stimulus looks like in both ECOG, I don't think they show any spiking information. I guess they do actually have the spiking, the evoked responses and the induced responses for the auditory cortex, for the layers as well. So, they're very, very careful to demonstrate what this data would look like under the best of circumstances. And it's great. It makes it a lot easier to follow for people that are not experts in necessarily auditory stimulus. I'm not an expert in auditory stimuli, so I can't really judge, let's say, the quality of the result, but I can say that the way they present it is very good for somebody that is not an expert in this specific area to interpret their electrical information. So they show us like how this paradigm makes sense for their setup.
So what was the significance? You as an outsider kind of in the auditory field, like what did you learn from this clean data?
Well, so there is a very interesting result. Auditory and electric setup. See, how should I say? It's interesting to me. It's interesting to me in the sense that if we're looking at these things in conjunction, I guess the way I saw it when we went over this the first time is we have no way of interrogating the rat to know how it is perceiving information. Okay. And this is a big argument in pretty much any perceptual field where, doing an experiment in a rat may not necessarily be the best way of doing that experiment. Not because the rat model doesn't work, but because we have no way of knowing what the rat is perceiving. So the interesting result to me was the fact in the auditory stimuli, they demonstrated that there was an induced response and an invoked response. Okay, so this is a normal circumstance for the rat. This is a rat that is, let's say, uninjured. There's nothing been modified about the network, or should not have been modified about the network aside from the presence of the shank, but we can make the assumption that we're not getting an induced response because the shank is present. It might be possible, but it's doubtful. And then we see this electric response. Now, comparing the electric response with the auditory response, we see part of the response is missing. It's not quite the same as we saw with the pure auditory response, right? So what does this tell us? This tells us that, the animal is not necessarily hearing the click. It doesn't interpret that, possibly, again, it may not be interpreting that as a click, but that click information is still being delivered. So I think Dr. Otto mentioned a single instance where we've done something similar in humans where we stimulated the auditory cortex, where we anticipated hearing, let's say, a tone, a single tone. And they said, well, they hear something of that frequency, but it wasn't quite a tone. And here, this is demonstrating, well, we can stimulate in those regions, not necessarily induce a click in the animal's perception, but still deliver useful information possible. Something like that. So, I don't know. The result was interesting. It kind of shows that our standard, simple microstimulations, and I say simple as in lack of complexity, not lack of difficulty, microstimulations aren't delivering the full gamut of information that we get from natural sensation. So it kind of pushes people to start trying more complex ways. Maybe we need stimulating along different sites or, simultaneously in different regions to generate the robustness of the auditory stimuli alone. That was the big takeaway for me. But again, I'm looking at it from more of a neuroprosthetic standpoint than a microstimulation network standpoint. I mean, this kind of demonstrates to the prosthetic community that we need more information-rich stimuli than we would give with a simple single microstimulus, let's say. So that was the key takeaway for me. You can see it when you see a comparison, the auditory and electric stimuli. When you see those run together, you see, there's a robustness of information that it's kind of lacking. There's frequencies that are missing, should I say? There's power missing from certain frequencies. And having that information and being able to do experiments like that is great. I mean, there's no other way around it. So.
And then we had a surprisingly long discussion about clicks.
Yeah.
I thought that was kind of funny. Do you want to talk about clicks and tones and what the difference is?
So from my limited experience with auditory stimuli, so the auditory cortex is tonotopic. Different regions are associated with different frequencies. When you, let's say, play white noise, you're going to activate a broad spectrum because white noise is... Okay, so the power of white noise is not evenly distributed throughout the spectrum, but you will still get activation on a broad range on the auditory cortex. Won't necessarily be even, but tones, if you have a pure tone and you can generate the proper gating and things like that, should only activate a single region of the cortex. And if you map it tonotopically, you should be able to say, well, this region versus this region is getting preferentially activated. Clicks, on the other hand, are closer in behavior to white noise. So if you think about looking at a stimulus in frequency space, so like an electrical stimulus in frequency space, it'll essentially a square wave, a very fast square wave, will blast frequency information through the entirety of the Fourier space. I mean, not entirety, but it'll blast frequency information from low to high frequencies in the Fourier space. If you think about a click is essentially an impulse. So a single square wave that you would see in electrical stimulus. So by perspective, it'll do the same thing. It'll still blast broad spectrum frequency information across the gamut. So essentially you're getting the same effect of white noise in a much shorter period of time. So
signals like louder, quote unquote, something like this, or instead of hitting like one key on a keyboard, you're just mashing the whole thing.
Pretty much. I mean, that's effective, like hitting all the keys on a piano. But yeah, so I mean, that's what the click does. That's what the tone, the click does, similar to white noise, but not quite the same.
Okay. Do you want to go through some of these figures and maybe explain them a little bit, or do you think, I mean, you weren't the one presenting this, of course, so you're just the most willing. But, so this wasn't exactly your, I guess, specialty, or this wasn't your, as you said, your field, but also you didn't really study it as in-depth as some of the other presenters.
No, I didn't. So
because it was pretty long. I don't know, the version I had was like 50 pages or something, 40 pages.
Wow. I did not realize it was... Oh, I don't know. Did you have the pre-press copy?
I think I had the pre-press one, yeah.
Yeah, that makes sense. So this one's formatted in a little more easy to read, easy to digest format. This is the one I looked at.
Yeah.
But going through all the figures might be
cumbersome. Cumbersome, yeah. 9 of them or whatever.
Yeah. I think at least for me, the big takeaway from my perspective was, what is this? Figure 5. So figure 5 is where, from my understanding of what was being done, is the more interesting information. So here, what they're doing is they paired the auditory stem and the electrical stem. And what they're looking for is where the, I guess, meeting point is. So where who contributed to what. Let's see. How can we cover this effectively? So let's say we add A and E. So they did auditory and electrical separate. Add them together and subtract them from the combination of the two. And what we should find is what the factors that were evoked from both of the stimuli independently are. I guess, if that makes sense. So what we're looking at is the difference of the individual with the whole. And we can see if, let's say, there's more information being presented or less information being presented. So I guess not necessarily less, but I mean, if there's what the change is, what adding electrical stimuli does to this. And for me, the big takeaway was that, there's, I guess I said it before and I'll reiterate, there's a complexity of the information that's just lost with the solely electric stimuli. And that was kind of what brought this back to what our work is, which is there's more information, there's more subtlety to the auditory stimuli than we see presented in figure 5 with just the solely electrical stimuli. And then the combination of the two adds to the richness of that information. So, I mean, it indicates that there's, a lot of higher level processing going on, a lot of processing in general going on in the information that we present to the brain through, I don't want to say natural means, but through, physiological means than necessarily electrical. So I know we covered a lot of the other figures, but we covered a lot of the other figures in accordance more with, trying to determine if they were doing something right. And I don't think anybody had any argument as to whether or not this was done correctly. It's an incredibly complicated surgery, incredibly complicated setup. So, I don't know, I think they did well. And I think the result that they present, at least for me, figure 5 is the most, poignant example of what it is that they're trying to demonstrate. So,
cool. I don't know. Any final thoughts or anything that you wanted to mention about this? Outside my wheelhouse, I'm not exactly sure too much about it. That's why I'm here, just to learn. But yeah.
Having attempted to do this in a more pared down respect, so not to this level, just demonstrate that we're getting a response in the cortex. Okay. Having tried to do that in the past, doing it to this level is incredibly difficult. I mean, it takes a lot of people that know what they're doing to get it done. And I don't personally know anybody that works in the auditory field, but I do know that the auditory field can be challenging to publish in because there's a million ways to do something wrong and only one to do it right. So yeah, I mean, if somebody with auditory neurophysiology experience could chime in, I would wonder what they would say. I'd like to get an expert opinion in this area specifically, because to me this looks wonderful. But again, to me this looks wonderful from a neuroprosthetic standpoint. That okay, so there's information that we're lacking, but we can get a lot of information in there to begin with. So yeah. I mean, I'm impressed. It's something like this is definitely a challenge, and doing it repeatedly is even more challenging. So
consistently,
yeah.
Cool.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.